So, as we had the previous class, we managed to look into the stress and strain, which is under a direct strain, a direct stress that we had. And I said also, it is going to be important that we do consider as a continuation working on the shear stress. As long we have the stress, like I said, the strain also has to be calculated. The stress and strain, they go hand in hand. So in this class, we are going to focus, or we are going to be measuring on the shear part, which is the shear stress. So the shear stress is now given by the symbol. We are going to be using the symbol tau to represent what? To represent the shear stress. Like I said, guys, these are just Greek alphabets that we are using. So that is for the presentation of what? The shear stress. And yes, we are going to notice other things later on. We'll see that one. So the difference now, remember when we had or when we worked with a condition where a direct stress is applied. We said when a force is applied to an elastic body, the force will deform or try to deform the body. We are going to notice a deformation, or it will try to deform, which is opposed now by this, which is totally different from the shear stress. Yes, a force is applied, but it is applied sideways to a material. And that force that is being applied sideways to that material, it causes the material to fracture. So this one, it causes the material to fracture or to distort. You see the difference. So let me just have it down. And we're just going to look into where it can be applied. So it is a force that is applied. Okay, that is applied sideways. So this one is applied sideways to a material. It is applied sideways to a material, and that causes the material to fracture. And that causes the material to fracture. So fractures actually to break, or that is to what? To distort. So that's the major part that we must consider. So situations where the shear stress can be actually applied, or where we say there is a shear stress. There are situations that we can say, okay, there is a shear stress. Which conditions that we can have this? We can have condition of wooden blocks attached by a nail. All right, you can have that part of wooden blocks attached by what? A nail. Attached by a nail. We can have a condition of a pin or bolt that carries a load. So we can have a pin, or we can have this one as a bolt which carries a load. Carries a load. There we can consider to say there is a shear stress. We can consider two plates that are being riveted together. Two plates which are riveted together. There we have got what? The shear stress. We can consider a beam that has a transverse or an extending gross load. A beam all right, that has a beam that has a transverse. It has a transverse load or an extended gross load, which is an example that we consider of from our statics, considering a cantilever. We can have these examples of materials which are being punched. Material is being punched. So for typical diagrams, guys, you can just use your Google search how diagrams are like, okay? Then we can have a pair of shears cut material. A pair of shears cut material. All these are under the influence, or they will cause the shear stress. So we must consider each and every one just to understand the basics, because yeah, somehow we might be given something which is not direct, but because of those situations, you know that, okay, this one cannot be a direct stress. It is what? It is a shear stress. So that is the major part. Then we are also going to consider calculations now of the shear stress, calculating of the shear stress. So as we consider the shear stress, we are going to be having two of them. All right. So let us just save calculating shear stress. So the shear stress can be calculated from a single shear or from a double. All right. So we can have two of them here, a single or a double. So let's say we have got a single shear stress, a single shear stress. So a single shear stress is going to be represented by the letter tau, of which, guys, this one depends with your textbook also. For us not to have confusion, you can just use the letter tau throughout. Okay? Like we said, stress, the letter tau. But when it is a single, the effect is on the area, guys. Here we are still on the stress. The calculation for the stress has not changed. Force over area. It's still the same thing, but all we are calling this shear. And when it is a single now, the area is just affected once. So there we are going to have our formula as force over area. Remember, like we had before, our area in square meters. This is going to give us the shear stress, which is measured in what? In pascals. So we can convert this to megapascals, depending with the best unit that we are going to have. But like I said before, it is best that we do have our conversions to megapascals, just like the previous classes that we had. I mean, the previous class that we had on the direct stress. So that's the single. Then when it is a double, we are going to also have a double. So of course, double shear stress. So depending also with the textbook that you are using, okay, some they use the capital letter T to indicate a double shear stress. It is up to you guys, but for just revision, just gonna use tau that we had before, or we can use capital letter T, like I said. That one, it depends, guys. The situation that is important here is double there. What is the effect? The effect will be on the formula. We are going to be having this as force over 2A, 2 times area. That is the major effect there. Nothing has changed. Our area in square meters, nothing has changed. Our answer in Pascal, which you can convert to the megapascal, and so on. So the conditions now, because it is not always where they are going to mention, if they do not mention, guys, that calculate the double stress, or they actually mention this condition where the double stress is this and that, you must know that you're dealing with what? A single shear. But it is not always where they do not mention about the double stress. Then you say, okay, this is a single. No. There are also conditions that you must be careful while you're working with what? A double shear stress. The conditions are that a double shear stress, it occurs where a pin joint is supported on both ends. These are the conditions. It is or occurs where a pin, okay, joint that is supported on both ends. So that is where we consider the clevis and hook, the major part that we are going to see. If they say we are given a clevis clip, you know that you are dealing with a double shear stress there. Double shear stress. So that is it, guys. Like I said, where a stress is, the strain is also there. So what will be the calculations on the strain? Because it is from what? It is from the shear stress consideration where the shear force is being used. You know, the consideration, guys, of a shear force. Just like when you've got a rectangular block like this, when a shear force is being applied, we're just going to consider a movement. We can have this part here moving, and we have it somewhere here. This part moving and having it somewhere here. So it can be something like this, where the base, where it was taken from here, is fixed. It remains where it was. These are the conditions of a shear. So we're just gonna have, okay, this is supposed to be same line here. All right, need this one to be under the same line like this. Only that the point has been, it is just like a slanting, a slanted. Remember those gates, the gates that we used to have, those old gates, that after some moment of time, you see the gate now slanted. It will remain, the base, it will remain where it was, but you just see a shift that has occurred on that gate that you were using. A shift. It is a shear. That is occurred. A rectangle to a parallelogram, we can consider that one as the best example of a shear. A square to a rhombus, best example again of a shear. So in this case, as we can consider the object that we had originally, it had its length, which is our original length. In this case, from this point to this point, that was our original length. But due to this shear stress, there is a part where an extension is from this point to this point. That is the change in length. Because we have the change in length. So in this case, all right, let's consider this one, the original length. Let's take this one. Let's use this one so that it can give us that angle part. Let us consider this way, okay? Meaning to say our change in length, our original length, if it is somewhere like this, it'll be a right-angled triangle that we have. Then in this case, this part here, which is, it was just like an angle, all right? Because of the small angles, I talked about the small angles when you're dealing with dynamics. That is where it was being taken from. But guys, do not go into deeper part of that. You okay? No problem. The change in length over original length is our formula always for strain. But as we consider, it is what? Shear strain now. Depending also with your textbook, some they can use the letter gamma, right? Some they can use the letter phi. So it depends also this one with your textbook. What are you going to use? All right. So using phi here. Okay. So like I said, this one, guys, can be used. It depends with the textbook that you are working with. The strain part there is the one that we are considering. Guys, the strain has not changed. Change in length over the original length, our formula as before. Same units. If you're using meters, work with the meters. If you're using millimeters, work with the millimeters. That is what we're going to have, guys. Extension over original length. We are done. So that is it. We do not want to waste much time there. Let us quickly have questions on this part. We are given, where necessary, use pi as what? 3.142. It is an instruction from your textbook. This is your source, guys. It is not an exam. You use that because you are using that textbook, or maybe it is an activity which was given in class. Then your teacher is telling you, guys, use pi as this. Don't fight that. Use the one that you're given. For exam, you work with what is for exam. If you are not given the value for pi, you use the one as it is on your calculator. All right. So anyways, number one, we are given, calculate the force needed to shear a pin. To shear, meaning to say there is a shear force, which causes what? A shear stress of 50 megapascal. So according to this information, we have got the shear stress. And it is just a normal, guys, a shear pin that is being applied. The stress is just a normal shear stress. This is not a double. It is a single shear stress. So we are given the single shear stress of 50 megapascal. All right. We are asked to calculate the force. In this case, we do not know the force, but we have got the 5 millimeter diameter of the pin, which is we can obtain the area from there. So like I said, guys, your formulas, they are in your hands. You can work whatever way that you understand. Remember the shear stress being force over area. What we need is the force. We're simply gonna cross multiply. So that is cross multiplying. Force is equal to the shear stress times what? Times the area. So this one we do not have the area. So we can calculate the area from what? Of the diameter, pi d squared over 4 in millimeters as it is. Then you just have to convert your answer, guys. Okay, no problem. Or you can just have in meters. It is up to you. That one is up to you. Okay, so this one I used the millimeters. So my answer is going to be in what? In a square millimeters. So that's 19,6375. So just use this one as it is, guys. And square millimeters. So as we are going to substitute on this formula, guys, remember the area is supposed to be in what? Square meters. Here you just use the units that you had, but do not forget on this formula, your area must be in square meters. So when converting, you must convert on the formula now. So there the shear stress is given 50 megapascal, 50 times 10 to the exponent of 6 times the area in what? In meters. So that's 19,6375 times 10 to the exponent of negative 6. Remember the conversion to square meters. You multiply by what? 10 to the exponent of negative 6. So that was going to give us the force that is required, which is the force needed to shear a pin. And that was 981,875 Newton. All right. So also just confirm with the values that you are obtaining from your calculator. So as we can see, guys, if you understand the basics of what we had in the previous class, this one is just a go through. The other part we are given, number 2, calculate the force needed to punch a hole 10 millimeters diameter. Calculate the force. Just like the previous question, so it's just like a repetition, this one, the force. All right, then we are given the diameter of 10 millimeters in a sheet of 3 millimeter thick metal. That is the part now. There is a thickness this time, which is 3 millimeters. When we are given a thickness, it is this is the idea now for when we've got the thickness, because what we need is the area there. What we need is the area. So it'll be like a condition where it is circular like this, but there's a thickness from one point another. There's a thickness that is in between the two circles. There's a thickness there of 3 millimeters. The thickness, it is just like a length, the length that is being taken. So in order for you to have the area, you cut this into a rectangular way like this, where you are going to take this way. The circle, remember we need area. So you're going to take this circle here. You need its length, which is its length is the circumference right around, because this is it, guys. You've got a circle like this. Okay, then you cut it at this point. It's just like let's put this way so that you can understand me. Let's say we have got a string, then you just cut it at one point like this. All right, it was a circular like this, then you cut it. You can stretch that string to be a straight line. You can stretch it to be a straight line like that. Anything that is circular. So the line, this one, is our length when it is in a rectangular way, like this is our length. The thickness is the width. This thickness from one circle to another, it is what? It is the width. As we can see, guys, this is the circle here, which is the same as the circle here. So that perimeter is the length, which is the same as the length here. The thickness is also here, the thickness. So this is the width. So it gives us this condition. It must be very careful on this one. It gives us this condition. So this length, if you take it from the circle, because it was a circle, it is the circumference of the circle now. So the length, since it is equivalent to the circumference of a circle, how do you calculate the circumference of a circle? That is pi d, or 2 pi r. Okay? The circumference of a circle. But what we need is the area. So if we now consider to say, okay, this is a rectangle, the area of a rectangle is what? It's length times width, where the length represents our circumference. The width represents the thickness. So therefore, we can say our area at the end of the day can be calculated as the length, which is what? 2 pi r or what? Or pi d, because we said length is equivalent to the circumference, which is what? Which is pi d. So in place of this length, we are going to substitute with what? With pi d times what? The width, which represents what? The thickness. That is where it is coming from, this formula, which represents the thickness now. So we are going to obtain the area now from this part. So you'll be having a formula from your textbook. You wonder where this formula is coming from. We take the circle. What does it actually represent? If we cut this one, we stretch it like this, it gives us a line, a straight line, which is just like a length. But that length, where was it? What was it actually represent? It was the circumference of the circle. So we must calculate the circumference, not the area. The circumference, the distance right around the shape, which is the circle. So that's it, guys. As we can see, the formula for area can be obtained. I just wanted you to be careful when you are to consider the area. So anyways, the question here was to calculate the force. We are given the maximum shear stress is given, which is 45 megapascal. So we need the force. So we saw these guys from the previous question that we had. We ended up with the force being the shear stress. If we manipulate that formula, the shear stress times what? Times area. So that was the major part. So we can calculate our area, as I said here from this formula pi. We are told, according to this information, use pi as this one. You use as it is, as you are given there. So our pi we are given as 3,142 times the diameter in millimeters, as it is 10 millimeters. So we have got this one as the length times the width, which is the thickness. Our thickness in millimeters, as it is 3 millimeters. So multiplying these guys, it was going to give us an area of 94,26. Remember, this is in millimeters. This is in millimeters. So our answer will be square millimeters. So converting that to be used on this formula, we must multiply by what? 10 to the exponent of -6. So that's our force. We're going to substitute. Let's save this one. 45 times 10 to the exponent of 6. Then the area. 94,26 times 10 to the exponent of -6. The square millimeters to what? To square meters. That was going to give us 4,241,7 in Newton. So that is how these questions can be given, as you just need to work out as many questions as you can as an individual. Try to do as many revisions as you can. And where we do not understand, that is where the membership plays a role. Let's join membership so that we can have more questions done in our favor. So that is it, guys. Till we meet again.